Okay, hello, multi. So what I want you to do is, first of all, say hello to Miss Boyer. Thank her for covering for me. I have a meeting. And just take out these notes here. What I want you to do is just follow my pen. Like I said, oh, by the way, the reason why there was no homework last night was because I left my iPad at school. No. So what you have today is you'll be doing this in class. You do have to stay in class, and then you'll do this, and then I'll also put homework on campus. Okay, but just follow my pen because I did pre-fill out to make the delivery more smooth. And please like. I'm trying to increase my likes. I would love to have likes. It just would make me feel so much more popular. I would love to have more than two, and those two are my own. Okay, vector basics. This should be comfortable and pretty swift. Okay, none of this is going to be new to you, but you want to do a full-on refresher, and so that's what we're going to do. Okay, vectors describe two things. They describe a magnitude, and they just describe a direction. Magnitude is like an amount of something, right? So I use the description like 5 miles per hour. That's just a magnitude. 5 miles per hour northeast, that sentence now is what's called a vectored quantity. It describes an amount, the 5 miles per hour, and it gives a direction. In the language of vectors, the magnitude is conveyed through the length of the vector, okay? And length of a vector is usually given like this notation: the magnitude of these double absolute value bars of magnitude of vector v, okay? I'll come here in a moment. So I'm going to go in 2D for a second. In 2D, you may recall vectors that are written in what's called component form. Okay, this is component form. The reason why component form is used often is because it's incredibly convenient. When you write a vector in component form, implied is that the initial point of the vector is the origin, and every vector has an initial point and it has a terminal point. Okay, so this vector v in 2 space has a component 7, 3. This is how you graph that vector. This is not array in geometry, right? Array in geometry implies going on forever, but in vector land, the length of the vector does matter. And you can probably see here a right triangle that is generated. So when I go back here, the length of that vector v would be the root of 7 squared plus 3 squared, okay? So maybe this vector here describes the speed of a rubber ducky, okay? And this rubber ducky is heading in this direction on a pond, this direction where the arrow is pointing, going at a speed of radical 52 miles per hour, okay? Okay. So that's just the very, very basic. Let's talk about how you express a vector. The most common is what I said. Vectors are expressed in component form, okay? In 2 space, there's a general vector A, comma, B. In 3 space, as you'd imagine, there's going to be 3 components of a vector, A, comma, B, comma, C. And if you go over here, okay, you'll have the X, Y, Z axes. You notice I just graphed a vector A, comma, B, comma, C. So this vector in 3 space, vector V, is pointing up into octant 1. That's what I'm trying to show here. Okay, of course, A could be A, B, C could be, non-positive as well. I just drew something that's most convenient. Component form is generally what I default to. It's the quickest for me. You'll also see vectors expressed in linear combination form. Linear combination form requires us to recall that there are 3 standard unit vectors, okay? Vector I, J, and K, and I definitely gave you these vectors in 3 space. Vector I is the unit vector, and I'll talk about that right now. I is 1, 0, 0. And if you go over here to the XYZ plane, 1, 0, 0 would be this vector right here, right? This vector I has a magnitude of 1. Vector J is 0, 1, 0. That's vector right here on the y-axis with a magnitude of 1. And then 0, 0, 1 would be this vector, vector k. It's a vector whose magnitude is 1 in the positive z direction. These are often referred to as the standard unit vectors, the 3 standard unit vectors. I know in physics you may use the notation, instead of vector I, you may use the notation I hat, you may use the notation j hat, and then k hat. I can speak either language. If you want to use those instead of these vector I and j and k, go right ahead, okay? So what is linear combination form? Well, if you see a vector v as a comma b comma c, if I write that vector in linear combination form, it looks like ai plus bj plus ck. In 2 space, if I want to express vector v in linear combination form, obviously in 2 space there's not going to be a vector k. So vector v in linear combination form here would be 7 vector I plus 3 vector j. And in 2 space, let's just make sure that we're clear here. In 2 space, vector I would just have 2 components, 1, 0, and then 0, 1, okay? I just noticed myself using the word component. In component form, when we talk about the components of a vector, this is the x component, this is the y component. Even when you have a vector in linear combination form, you can still be referring to the x component of the vector and the y component of the vector. So just wanted to make sure that I clarified that vocabulary word, okay? Okay, vectors are equivalent if. Equivalent vectors have the same magnitude and the same direction, okay? So go up here for a minute, right? You see this vector v. I can pick up this vector, I can move this vector around, right? As long as my vector has the same length and direction, those vectors are equivalent. So all of these vectors that I'm drawing, they are all equivalent. They all describe the exact same thing. Some people like to say, oh, if vectors are parallel and pointing in the same direction and the same length, they are equivalent. And I am fine with that. Just be careful because, right, if they are not in the same direction, they are not equivalent. I'm okay with you saying parallel, but you have to add the additional details. Parallel and the same length and pointing in the same direction, okay? So if you have an initial point, if vector u, we're going to go in 3 space, let's say vector u has an initial point of 2, negative 3, 4, and a terminal point. Let's first express vector u in component form, okay? Let's just make sure we understand how to do that. When you take a vector that is described not in component form, and generally speaking, the way that you describe that vector is a bit verbose. You have to tell the reader where the vector begins and where the vector ends, okay? When you want to describe this vector in a much simpler form, you're going to express it in component form. And the way you do that is you take terminal x-coordinate minus initial x-coordinate, terminal y-coordinate minus initial y-coordinate, etc. So vector u I'm going to rewrite as this. Okay? Now I have just expressed vector u, and notice I did not rename the vector. They're exactly the same vector. This vector is identical to this vector, okay? So what I've done is just renamed this vector in component form. When you are adding vectors, when you do the operation is fairly straightforward. Adding vectors involves just adding corresponding components. So if this is vector u, if this is vector v, when you add the vectors, you get vector 1, 7. That's just the procedural. The geometric interpretation of adding is important. Okay, let me first give you some vocabulary. When you are performing an operation between vectors, like this is the operation here, the result of that operation is oftentimes referred to as the resultant vector, okay? This is the resultant vector. And what a resultant vector is merely what it sounds like. It's the vector that results from whatever operation was being performed. So again, I think most of this screencast, my guess is you will, it'll be either very comfortable or even in some cases you may even know this. So what I'm going to do here is just graph vector u and v individually. Okay, here's vector u, this is vector u, boop, then vector v is here. Doot, 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 doot. Doink. There's vector u and there's vector v. Okay? When you add u and u plus v, what's happening is you're doing a head-to-tail addition. Geometrically, when you add vectors, here's what you do. U plus v means I'm going to sketch vector u, and then I'm going to put the initial point, whoops, I think I just misnamed. That should be vector v. Oh, yam. Doink. Boop. Boop. Okay. When you add u plus v, you're saying geometrically u plus v. U plus v. So when you add vectors, what you do is you add the tail. So this is it's called head to tail, right? This is the head of vector u, and then you take the tail of vector v and you add it to it, okay? And here's what's going to happen. I'm going to do it right here, right? So what's u plus v? U plus v looks like this. Here's vector u. I'm going to add to it vector v. That's vector v. Okay, and what is the result? The result is this. The result is you start at the tail of vector u and you draw the vector up to the head of v. This red vector right there, that is the vector u plus v. Okay, that is the vector 1, 7. So the resultant vector, I've seen various phrases for vector addition. It's like a parallelogram effect, right? U plus v. And as you can see, u plus v, when you're adding two vectors, vector addition is commutative. So u plus v does equal v plus u. Okay, so that's u plus v. Very good. Okay, a vector multiplied by a scalar has the effect of, first of all, what is a scalar? Okay, a scalar is, right, the scalar is the same thing as what's called a scalar factor. Let's take a look at an example. If you have vector v, which is 2, 1, 4, okay, follow my pen, not the screencast, follow my pen, okay? And if I want to say, well, what's 3 times vector v? This constant you're multiplying by vector v, that's referred to as the scalar factor. In text, they'll often refer to that number as k. So k is the scalar factor. When you multiply a vector by a scalar factor, what you merely do is just multiply each of the components by that scalar factor. So you get 6, 3, 12. What is the effect of multiplying a vector by a scalar factor? Well, let's see. So here's vector v. And notice that the vector v has a magnitude of radical 21. Well, if you multiply a vector by a scalar, what that does is it multiplies the original magnitude by that scalar. So the magnitude of 3 vector v is going to be 3 times radical 21. And as you can imagine, if k is positive, right, the result, right, the relationship between v and 3v is that they're still pointing in the same direction with different magnitudes. If k becomes negative, and that just changes the direction perfectly oppositely. So k being less than 0 will result in a vector that is oppositely directed to the original vector. And of course, if k equals 0, what that does is it results in what's called the 0 vector, which I always found very funny. When you multiply a vector by 0, what that does is it creates a point, which is we call the 0 vector. Okay? A very common operation you will do in multi, almost to the point where it'll be just natural, is you'll often normalize or unitize a vector. Okay? And what that means is taking a given vector v, and finding a vector parallel to it and the same direction, okay, but with magnitude 1. Okay, so here's an example. So here's a vector v in 3 space, and you know vector v has that magnitude, okay? If I multiply a vector by 1 over its magnitude, so this is a very common operation you will do here, a vector multiplied by 1 over its magnitude will result in a vector here that is the exact same direction as vector v with a magnitude of 1. And having a vector of magnitude 1 is going to simplify our lives and computations immeasurably as we go and move further into multi. Okay, so right now you can't really see why this is going to be helpful for us, but I promise you will. Okay, at this point, page 1 here just covers the basics. Isn't that beautiful? Oh, it's so pretty. I would like you to take a deep breath and just look around and give someone a compliment, and then come over here to page 2, okay? Right now in class, go ahead. You can work together, just 1 through 5. This is just basics, okay? Once you finish 1 through 5, just scroll on down or keep playing me here for the answers, but please do not do this. Please just don't continue playing me. Just so you can see all the answers. I'm going to go there right now. So pause me at this point, work on these, and then go ahead and check your answers. So here are the answers. I don't think 1, 2, and 3 require much in the way of any kind of conversation. I think, and this is not for question 3, so hold on. I'll go ahead and explain question number 4, which is really fun, okay? So you have the vector 4, 2, 3, right? Yeah, which is the result of adding the 2. And it's saying find the acute angle that vector makes with the positive z-axis. So here's, I'm going to zoom in for a minute, okay? So this is actually, it just requires a little bit of visualization. So vector v is kind of pointing up here in octant 1. And what I just did was I just created a right triangle with the positive z-axis. And when I quote-unquote drop an altitude, if you will, drop an altitude from the head of v to the z-axis to create this right angle, what I get here is a length of 3. And you know the length here is radical 29. And a little right triangle trig can allow you to find theta. Okay, so there's 4. Okay, now use calc. And then let's see what happened here. I think 5, again, no need for much in the way of explanation. Okay, that is it. Your homework is on vector basics. I'm going to go over dot product, and I know you all saw dot product in Math 2 or even Math 3. I don't know that you ever did the geometric definition of it. And then, of course, we're going to go right to 3 space and orthogonal projection. So when I see you again on Monday, we'll get into some new stuff. But for now, you can go ahead and start your homework. Goodbye, multi.